the South Pole of time. Picture sitting on the quiet edge of a vast, motionless body of water late at night. The air around you is still. There is no wind to ripple the surface, no sound except the soft, rhythmic murmur of water meeting the shore. Up above, the canopy of the night sky stretches out in absolute silence, dotted with distant, faint silver points of light. It feels permanent, as though this expanse has existed forever, stretching backward into a memory without a beginning. Yet, when we look up into that dark blue abyss, we are looking back through time. Light takes time to travel. The glow from a distant star reaching your eyes tonight left its source millions of years ago. Step by step, light guides us backward past newborn stars and sprawling galaxies until we reach a boundary in the deep dark. There is a question that naturally settles into the mind when the world goes still. What lay before all of this? It is a question that feels simple when whispered into the night. But as modern physics has discovered, it may be a question that defies a complete answer. The further back we trace our story, the more our standard rules of intuition begin to gently soften and dissolve. We often imagine the origin of our universe as a sudden, violent event, a spark igniting in an empty void. Popular culture calls it the Big Bang. We tend to visualize a tiny, brilliant ball of light hanging in a dark room, suddenly detonating and spraying matter out into the surrounding darkness. In modern cosmology, the reality is far more subtle and strange. The Big Bang was not an explosion of matter moving through an existing space. Space was not a stage sitting empty, waiting to be filled. Instead, it was the expansion of space itself. Think of an endless fabric, soft and stretchable, pulling outward everywhere at once. There was no center to this expansion, no outside edge, and no empty room into which it expanded. Every point in space was simply growing further apart from every other point. In those earliest moments, roughly 13.8 billion years ago, everything that would ever form stars, planets, oceans, and living beings was compressed into an unimaginably dense, hot state. Space was filled entirely and uniformly with energy. As space expanded, it cooled. The initial hot density smoothed out, stretching into the vastness we see today. That expansion continues to this day, carrying distant galaxies further apart across the deep night. For a long time, the universe contained no stars to light the dark. No planets circled suns. There was only an expanding expanse of warm energy, cooling patiently across a sky that had not yet learned how to sparkle. When we try to peer further back toward that initial moment, we reach a point where our current understanding begins to fail. We naturally ask what happened before that expansion began. What existed the day before the Big Bang? To our human minds, tuned to the flow of ticking clocks and rising suns, time feels like an endless river. We assume that no matter how far back you walk along the bank, there must always be a stretch of river further upstream. Albert Einstein changed how we understand this flow. Through his theory of general relativity, he showed that space and time are not separate entities. They are woven together into a flexible fabric called spacetime. Matter and energy bend this fabric. Where gravity or density is immense, time itself slows down. If you trace the expanding universe backward, like a film played in reverse, space shrinks down toward a state of infinite density, a point known mathematically as a singularity. At this boundary, the geometry of spacetime curves so sharply that our equations cease to work. Stephen Hawking once suggested a simple way to picture this limit. Picture walking south across the smooth curve of the Earth. As you step further south, the lines of longitude draw closer together. Eventually, you reach the South Pole. If someone asks you, What lies 1 mile south of the South Pole? The question loses its meaning. It is not that a wall blocks your path. It is simply that the direction south terminates at that point. The South Pole is where south begins. In a similar way, time itself may have emerged alongside space at the Big Bang. If time began with the origin of the cosmos, then asking what happened before the Big Bang might be like asking what lies south of the South Pole. There may be no before. The question itself rests on an assumption that time has always flowed. And yet, physics does not rest easily at a singularity. Infinite density is often a sign that our theories are incomplete. General relativity describes the universe on the largest scales, galaxies, gravity, and cosmic curvature. But when the universe was smaller than an atom, another fundamental set of rules took over, the strange world of quantum mechanics. As space grows quiet, our classical rules fade. The smooth river of time begins to break into tiny, uncertain ripples, leading us from the grand geometry of space into the microscopic realm where the cosmos was born, the quantum engine, and the first light. In our daily lives, empty space seems truly empty. A vacuum feels like total nothingness. But in quantum physics, nothing is surprisingly active. On the smallest possible scales, space is governed by quantum fluctuations. Energy cannot remain perfectly still or precisely zero. Instead, tiny ripples of energy constantly fluctuate, borrowing existence for fractions of a second before vanishing back into the background. Even in a complete vacuum, space softly hums with potential. Consider the microscopic landscape of the primordial cosmos. In a state where macroscopic time and space as we know them had not yet taken shape, a subtle shift in quantum fields could have triggered a runaway process, transforming a subatomic ripple into a vast cosmos. This leads us to the concept of cosmic inflation. In the briefest fraction of a second after the initial moment, space itself may have undergone a breathtakingly rapid stretching. The fabric of space expanded exponentially, far faster than light travels through space, without violating the speed limit of matter within it. This inflation smoothed out any irregularities, leaving space flat, uniform, and immense. When inflation came to a halt, the energy driving it converted into heat and particles, the primordial soup of light and matter. The microscopic quantum ripples that existed before inflation were stretched across light years. Those tiny fluctuations became the seeds of gravity. Over billions of years, they drew gas together, forming the delicate webs of stars that illuminate our view today. An ocean of particle light, calm and undisturbed, holding within its warmth the blueprint for every world that would ever be born. This early light is not just a theoretical idea. It left behind a physical signature that we can observe today, the cosmic microwave background radiation. If you tune a sensitive radio telescope to the quiet gaps between frequencies, you pick up a faint, uniform hiss coming from every direction in the sky. This is the thermal echo of the early universe. Light released when space was just 380,000 years old. It is the oldest photograph of the cosmos in existence. When scientists mapped this radiation with space telescopes, they discovered subtle temperature variations, differences of just a fraction of a degree. These tiny temperature ripples line up precisely with the predictions made by cosmic inflation theory. The microscopic quantum fluctuations of the primordial world are written directly into the temperature of the night sky, while cosmic inflation successfully accounts for the flatness, uniformity, and microscopic seeds of structure we observe today. It opens the door to deeper questions. If inflation could happen once, did it happen everywhere? Was the Big Bang a unique, solitary moment of creation? Or was it merely one localized event within a far broader, more complex cosmic engine? endless oceans and the boundaries of knowledge. Instead of a single line with a definitive start, picture a slow breathing cycle. In cyclic universe models, reality goes through long eras of expansion, gradual cooling, and eventual renewal. One version of this concept is known as the Big Bounce. In loop quantum gravity, a theory attempting to unify quantum mechanics with Einstein's general relativity space, is not a smooth, continuous fabric. Instead, it is made of tiny, indivisible units of geometry. Because space cannot be squeezed down to absolute zero volume, a collapsing universe cannot shrink into a singularity of infinite density. Now suppose a previous universe collapsed under the pull of gravity. As it reaches a maximum physical density limit, the quantum structure of space resists further compression, acting like a compressed spring. When compressed to its absolute limit, space rebounds, triggering a new era of cosmic expansion. In a Big Bounce scenario, our Big Bang was not the moment reality popped into existence out of nothing. It was simply a transition point. The moment a previous universe rebounded into our own. The flow of time did not start at a single point. It may have been flowing through an endless series of cosmic breaths. Another possibility arises directly from cosmic inflation itself, the concept of eternal inflation. In many mathematical formulations, inflation does not stop everywhere at once. It stops in small, isolated patches, while the space between those patches continues to expand exponentially. Picture a boundless, peaceful ocean of expanding space. In certain spots, inflation slows down and settles, dropping its energy into heat and matter. A localized universe forms, stable and filled with stars, much like our own. Meanwhile, outside our observable region, the vast inflation field continues to stretch. Elsewhere, another region cools, and another pocket universe is born. Endlessly. This is the multiverse hypothesis. In this view, our entire observable universe, everything we can detect across 46 billion light-years, is merely one quiet puddle in an infinite landscape of pocket universes. Each might have its own distinct physical constants, its own subtle variations of gravity and light. Sir Roger Penrose offered another distinct mathematical model known as Conformal Cyclic Cosmology. Penrose focused on the far future of our universe. Trillions of years from now, long after the last stars have burned out their fuel and black holes have slowly evaporated away, the universe will consist almost entirely of massless particles like photons. Particles with no rest mass do not possess a frame of reference that measures proper time or distance scales. To a universe populated entirely by light, a vast, cold, infinitely stretched space becomes geometrically identical to an extremely dense, hot state. When scale disappears, the cold, empty end of one universe smoothly maps onto the hot, dense Big Bang of a new era. Epoch after epoch passes, with each cosmic era leaving subtle rings of radiation imprinted on the microwave background of the next. Between these vast cycles, space rests in total stillness. No clocks mark the passage of time, yet the potential for matter and light waits patiently in the quiet structure of geometry. These theories are breathtaking in their imagination and mathematical structure. Yet, it is essential to distinguish between what we know with certainty and what remains hypothetical. The core framework of the Big Bang, that our universe was once hot and dense, and has been expanding for nearly 14 billion years, is established, verified science. It is confirmed by the expansion of space, the abundance of light elements, and the faint glow of cosmic background radiation. However, theories like eternal inflation, the Big Bounce, the multiverse, and conformal cyclic cosmology remain theoretical frontiers. They are mathematical models that attempt to bridge the gaps where our current laws break down, waiting for future experimental data to test them. Modern physics stands at a humbled frontier. We do not yet possess a tested, unified theory of quantum gravity, a single framework that unites the vast geometry of space with the uncertain world of the atom. Until we find that missing piece, the ultimate truth of what lay at the very beginning remains hidden behind a veil of mathematical uncertainty. Yet, this uncertainty is not a failure of science. It is a testament to the scale of reality. When you look up at the dark horizon tonight, the faint starlight reaching your eyes carries the physical imprint of processes that began billions of years ago. The cosmos is not a finished story locked in a book. It is an active, evolving expanse whose deep mechanics we are only beginning to decode. The night sky remains open and undisturbed. The stars continue to shine in silence, drifting along the calm, expanding paths of space, carrying their ancient light into the quiet of the future. The arrow of time. Now suppose you are standing in a dark room, watching a crystal glass drop toward the floor. It strikes the ground and shatters into 100 gleaming fragments. You have seen this happen 1,000 times in ordinary life. The sequence feels natural, unquestioned, and final. Yet, if you were to watch that same moment played in reverse, the scattered shards lifting from the floor, drawing together seamlessly, and reforming into a whole unbroken vessel, your mind would instantly recognize something unnatural. You would know, without hesitation, that the tape was running backward. In our daily existence, time moves relentlessly in a single direction. We age. Leaves fall from trees and decay. Stars consume their nuclear fuel and slowly dim. The past is fixed in memory, while the future remains an uncharted expanse of possibility. Physics calls this one-way progression, the arrow of time. What makes this arrow so deeply mysterious is that, at the microscopic level, the fundamental laws of physics do not seem to care about the direction of time. If you examine the mathematical equations governing the collisions of atoms or the paths of light, they work with equal perfection whether time moves forward or backward. A subatomic particle bouncing off another looks physically valid in either direction. The basic laws governing gravity, electromagnetism, and quantum mechanics are symmetric with respect to time. Why then, on the grand scale of our cosmos, does time only ever flow forward? The answer lies not in the laws of motion, but in a property of energy and matter known as entropy. Drop a single drop of dark ink into a glass of still water. At first, it hangs in the clear liquid as a concentrated cloud. Over time, without any pushing or stirring, the ink gently diffuses, spreading its color evenly until the entire glass settles into a uniform shade. Entropy is a measure of disorder, or more precisely, a measure of how many different ways the microscopic parts of a system can be arranged without changing its overall appearance. There are very few ways for ink particles to remain tightly clustered in a single drop within water, but there are countless trillions of ways for those same particles to be scattered throughout the glass. Nature naturally drifts from order toward disorder simply because there are far more ways to be disordered. This principle is enshrined in the second law of thermodynamics. In any closed system, overall entropy always increases over time. When applied to the entire cosmos, the implications are profound. The universe is a closed system. The reason time moves forward, the reason broken glass does not spontaneously assemble itself, is that the universe is constantly moving from a state of lower entropy to a state of higher entropy. This leads us back to the mysterious origin of space itself. For entropy to be increasing today, nearly 14 billion years after the Big Bang, the universe must have begun in a state of extraordinarily low entropy. In those initial moments, matter and energy were distributed with exquisite smoothness, held in a state of immaculate structural order. Every galaxy, every star that burns in the night, and every breath taken on Earth is powered by the gradual, steady decay of that initial, primordial order. We are living in the long, quiet wake of an exceptionally ordered beginning. Consider the stars drifting through the vast dark. Each sun is an engine of low entropy, radiating light out into the quiet cold, slowly scattering its concentrated warmth into the endless night. As time flows forward along this thermodynamic path, gravity adds a fascinating twist to the experience of time itself. In Einstein's universe, time does not tick at a uniform rate everywhere. It flows at different speeds depending on where you are and how fast you are moving. Where gravity is vast, space and time are bent more severely, and the passage of time gently slows down. If you were to hover in a vessel near the edge of a supermassive black hole where gravity stretches space to its extreme limit, clocks on board your ship would tick far more slowly than clocks on a planet far away in deep space. To you, sitting inside the vessel, time would feel entirely normal. Your pulse would beat at its usual rhythm. Your thoughts would move at their ordinary pace. But if you looked out through a viewport at the universe, far beyond the black hole's gravitational field, you would see the outside world moving in fast motion. Star lifetimes would unfold in years instead of eons. Galaxies would swirl and evolve like swift currents in a river. Gravity stretches the fabric of space-time, demonstrating that time is not a rigid, universal metronome beating across the void. It is a flexible dimension, interwoven with space, stretching and curving in response to matter and energy. Yet, despite these local warping effects, the overarching arrow of time continues its quiet, irreversible journey forward. Where is this long journey leading? If the second law of thermodynamics holds true across cosmic scales, the far future of our universe is defined by the eventual exhaustion of available energy. Trillions of years from now, stars will exhaust their hydrogen fuel. One by one, the glowing suns that illuminate our night sky will dim and go dark. White dwarfs will slowly cool into cold iron spheres. Black holes will hold the remaining mass of galaxies for unimaginable ages, before slowly evaporating away over timelines that dwarf our current understanding. Eventually, space will reach a state known as thermal equilibrium, a quiet state of maximum entropy, often called the heat death of the universe. In this far future, temperature will be uniform everywhere. No energy gradients will exist to power stars, fuel chemistry, or drive the engines of life. Space will be vast, calm, cold, and still. When thermal equilibrium is reached, entropy can no longer increase, because disorder has reached its maximum. And when entropy can no longer change, the thermodynamic arrow of time loses its direction. Time, in any meaningful physical sense, ceases to mark the passage of events. Imagine that distant cosmos, a vast, silent ocean of light and space resting at absolute peace, where no change occurs and no clocks mark the quiet expanse. Yet, as we explored when looking at the cycles of creation, even absolute maximum entropy may not be the final word. In frameworks like Conformal Cyclic Cosmology, that far future state of massless light loses all sense of scale and distance, mathematically reshaping itself into the low entropy boundary of a newborn cosmos. What appears to be a final, cold ending may simply be the quiet geometry required to trigger a new beginning. We do not yet know if time is an eternal line stretching endlessly into the dark, or a vast, breathing geometry that weaves cycles beyond our current sight. What we do know is that our present moment is a quiet privilege. We exist in a moderate era of cosmic history, an age where the universe is neither too hot nor too cold, where stars still burn bright, and where intelligent minds can look up into the dark sky to ponder the flow of time that carries them. The night sky remains undisturbed and deep. The stars continue their slow, silent fusion, casting their ancient light across light years, marking another calm moment in the unfolding history of space. In the next chapter, we will leave the mysteries of deep time and turn our attention to the cosmic web itself, exploring how invisible matter and phantom energy shape the structure of the universe, weaving gas and light into the vast galactic architectures we observe today. The breathing cosmos. Picture a darkened room lit only by the steady, motionless flame of a single candle. Watch it closely. The flame draws oxygen from the air, steadily consuming its wick as time moves forward. In our ordinary experience, a candle burns down until its fuel is exhausted, leaving behind a hollow room. It does not reignite itself. It does not rise from its own ashes. For over a century, modern cosmology viewed the universe through a similar lens, a one-way story with a dramatic beginning, a long, cooling middle, and an endless, cold conclusion. Yet, throughout human history, another intuition has existed alongside our science, the rhythm of cycles. Seasons return after winter. Oceans rise and fall in steady tides. Stars are born, fade, and seed the vast clouds from which new suns emerge. In theoretical physics, this ancient intuition takes shape as the cyclic universe hypothesis. The idea that our cosmos is not a single, finite sentence, but an endless, rhythmic poem. The foundation of cyclic models rests on a profound challenge to standard Big Bang theory. What if the initial moment was not the start of existence itself, but simply the turn of a cosmic page? In traditional cosmology, tracing space back to time zero leads to a singularity, a point where density becomes infinite and known laws cease to operate. Cyclic models attempt to bypass this boundary, replacing a destructive point of creation with a continuous transition. One of the most compelling modern versions of this idea comes from string theory and extra-dimensional physics, known as the ekpyrotic model. Consider two vast, weightless sheets floating parallel to each other across an unseen higher dimension. Expansive boundaries of space known to physics as branes. In this framework, our four-dimensional universe, comprising 3 dimensions of space and 1 of time, exists on one of these vast sheets. A second sheet floats nearby, separated by a subatomic gap across an invisible dimension. For long eons, these two branes drift apart, unruffled and cold. Within our own sheet, space expands, suns exhaust their nuclear fuel, and matter dilutes across light years. Space becomes vast, sparse, and clear. Eventually, the subtle attraction pulling between the two sheets draws them slowly back together. When they meet, they do not collide like solid objects. Instead, they make soft contact across their entire surface at once. This contact releases an immense surge of potential, converting kinetic energy into a hot, uniform soup of particles across our space. To an observer living within our universe, that moment of contact feels indistinguishable from a Big Bang. Space is instantly filled with heat and energy. Expansion begins anew. The two sheets then bounce apart, drifting back into the higher dimensional gap. As they separate, our cosmos cools, gas collapses under gravity, and new galaxies organize themselves across the sky. Imagine floating between those two vast dimensional sheets in the deep eons before they touch. No stars yet exist. There is only an unblemished void, holding its breath in complete stillness before the warmth returns. What makes cyclic models mathematically compelling is how they address the uniformity of our sky, without requiring a sudden, violent expansion like inflation. When we look across 46 billion light-years in opposite directions, the background temperature of space is nearly identical everywhere. In standard cosmology, explaining this requires a brief fraction of a second where space stretched faster than light. In a cyclic model, this uniformity is achieved naturally during the long, cold contraction phase before the bounce. During that eon of preparation, as the universe slowly prepares for the next cycle, space has eons to stretch and equalize its temperature. The balance we observe in our sky today may not be a relic of a sudden explosion, but the memory of a previous universe settling into stillness before the next epoch began. Furthermore, microscopic quantum ripples present on the sheets before they touch are stretched across space. When the sheets make contact, those tiny fluctuations become imprinted into the hot plasma ripples that could ultimately trace their origins to the eons before our Big Bang occurred. A slow, ancient breath. An expanse stretching long into the cold, clearing its sky before drawing back in to begin again. Yet, the cyclic universe faces a formidable obstacle rooted in thermodynamics, the accumulation of disorder. Every generation of stars, black holes, and radiation produces entropy. If a universe carries its accumulated disorder over from one cycle to the next, each new epoch would inherit the heat and debris of the past. Tracing this series backward would still lead you to a definitive first cycle, a true beginning. For a cycle to repeat endlessly, space must find a way to clear its stage. Modern cyclic theories propose a subtle solution. Cosmic expansion itself acts as a natural filter. During the vast eons of expansion between collisions, space stretches so immensely that the density of old matter and dead stars drops to near zero. By the time the dimensional sheets prepare to touch again, the region of space that will form our observable cosmos has been cleared of almost all ancient structure. The local disorder drops, leaving a clean stage for a fresh burst of primordial warmth. Picture an ocean whose waves rise, spread across an unbroken shore, and recede, leaving the sand immaculate for the next tide. Despite its mathematical elegance, the cyclic model remains speculative. While it offers alternative solutions to the problems of standard cosmology, it relies on extra dimensions and forces that have not yet been observed in physical experiments. Scientists continue to search for distinct signatures, such as specific gravitational wave patterns that could one day distinguish a cyclic universe from a single origin. Whether our universe is a singular journey or one movement in an endless cosmic rhythm, the cyclic hypothesis invites us to reconsider the scale of physical law. The elements that form our world, our oceans, and our thought tonight may be part of an ancient tapestry energy that has taken many forms over eons, waiting through cold eras before rekindling in the light of a new sky. The night sky remains motionless, holding its deep silence. Far out in the velvet dark, distant stars continue to burn, carrying their light forward across space, marking another quiet moment in the unfolding geometry of reality. As we look deeper into the subatomic structure of space itself, another possibility emerges. One where space is not a smooth sheet, but a woven network of quantum threads capable of bending, compressing, and rebounding like a spring. The quantum spring. Imagine holding a finely woven silk tapestry between your hands. From a distance, it appears as a single, unbroken surface, smooth, continuous, and seamless. Pass your fingers across it, and you feel no breaks or boundaries. Bring that fabric close to your eyes, and the illusion vanishes. You begin to see individual threads interlaced in a precise grid of overlapping loops. The fabric is not a continuous entity. It is a tapestry made of distinct, finite parts. For centuries, Physics treated space itself like that distant silk tapestry, a smooth, continuous background stretching endlessly across the void. Albert Einstein's general relativity described space as a flexible sheet that curves under the weight of planets and stars. But in Einstein's equations, space remains smooth. You can divide a meter of space into smaller and smaller fractions without ever hitting a fundamental limit. When applied to the origin of the cosmos, this smooth model creates a severe mathematical breakdown. If a collapsing universe shrinks down towards zero size, a continuous fabric compresses into a point of infinite density, a singularity where reality terminates. Loop quantum gravity offers a different perspective. It asks a radical question. What if space is not smooth at all? What if space, like matter, is made of indivisible atomic units? Picture drifting down into the subatomic realm, past molecules, past atomic nuclei, down to the absolute shortest limit of length. The Planck scale. There, the smooth illusion dissolves into an interconnected network of woven geometry. In this quantum picture, space is constructed from tiny loops of gravitational field, woven together into a dynamic foam. You cannot have half a loop of space, just as you cannot have half an atom of gold. Space has a fundamental grain. Because space has a minimum possible unit of volume, it cannot be compressed down to absolute zero. It possesses a built-in physical limit. Now suppose an earlier universe were collapsing under the unrelenting pull of its own gravity. In classical physics, that collapse would continue indefinitely until every galaxy, star, and particle was crushed into a mathematical point. But in loop quantum gravity, as the universe shrinks toward the Planck density, the microscopic geometry of space begins to resist. When compressed near its ultimate limit, the granular structure of space-time acts like a tightly wound steel spring. Gravity, which is normally an attractive force, turns sharply repulsive at extreme densities. The collapse slows down. It comes to a brief, motionless halt at a maximum physical density. Then, instead of terminating in a singularity, the compressed cosmos rebounds. This is the Big Bounce. Visualize that motionless instant at the bottom of the bounce. A vast, dying universe compressed into a subatomic sphere of raw potential, pausing for a fraction of a heartbeat before unfolding once again into light. In a Big Bounce scenario, our Big Bang was not the moment space was created out of nothingness. It was a cosmic transition, a moment where a contracting past uncoiled into an expanding future. The transition from bounce to expansion happens smoothly. The tremendous energy stored in the compressed geometry releases, driving a surge of primordial energy that expands outward, cooling as it stretches across the void. What makes this quantum spring model particularly fascinating is how it handles physical information. As a previous cosmos contracts, its large structures, galaxies, stars, and planets are crushed and dissolved by extreme density. Yet, quantum correlations might survive the bounce. Subtle patterns from the old universe could pass through the compressed spring, leaving delicate traces imprinted on the density fluctuations of the newborn cosmos. The subtle ripples we measure in the cosmic microwave background today might carry the microscopic echo of a world that existed before our bounce occurred. A deep ocean floor after a storm, where ancient currents have settled into motionless sand, holding the faint outlines of waves that washed over the water eons ago. Despite the mathematical elegance of loop quantum gravity, the Big Bounce remains an unproven theoretical model. Because the Planck scale operates at energies vastly beyond the reach of our largest particle accelerators, testing the granular nature of space directly remains one of the greatest experimental hurdles in physics. Researchers look instead to the sky, searching for faint clues in primordial radiation that might distinguish a quantum bounce from a standard inflationary birth. Yet, the idea of a quantum spring shifts our fundamental relationship with the origin of time. It replaces an absolute wall with a bridge, suggesting that geometry itself possesses a built-in resilience that prevents reality from collapsing into nothingness. The sky above remains undisturbed and dark. Countless stars burn brightly in the velvet expanse, guiding our eyes across light years, marking another calm epoch in the ongoing story of space. The endless ocean. Sit beside a still mountain lake as a gentle rain begins to fall. Watch the surface of the dark water. A single raindrop strikes the surface, creating an expanding circle of ripples that glides outward across the water. A moment later, another drop lands a short distance away, forming its own expanding circle. Then another, and another. Each drop creates a localized region of activity, while the lake around them remains dark and expansive. In theoretical cosmology, this image mirrors one of the most remarkable consequences of cosmic inflation, the concept of eternal inflation. In earlier chapters, we explored how inflation describes a brief period of rapid expansion in the early universe, a moment where space stretched exponentially, smoothing out irregularities and seeding the cosmos with energy. In standard introductory science, inflation is often presented as an event with a uniform start and finish. The entire cosmos inflates, stops inflating everywhere at once, and converts its energy into a hot plasma of matter and light. However, when physicists examined the quantum mathematics governing the inflation field, they discovered something unexpected. According to many inflationary models, inflation may be easy to start, but nearly impossible to stop everywhere at once. Consider a boundless, high-energy landscape stretching in every direction. A sea of raw potential expanding exponentially, doubling its volume every fraction of a second. The field driving cosmic inflation is governed by quantum mechanics, which means it is subject to random fluctuations. In most of this inflating sea, the quantum energy remains high, forcing space to continue expanding at exponential speeds. Imagine drifting through that endless, inflating sea. A place without stars, sound, or matter, where space itself rushes outward so quickly that no light could ever span the distance between 2 points. In small, random patches of this inflating expanse, quantum fluctuations cause the energy level to decay, rolling down like a ball coming to rest at the foot of a hill. When the inflation field drops in one of these localized patches, inflation comes to a halt in that specific region. The energy stored in the field converts into heat, light, and matter. A localized universe is born, a self-contained bubble, filled with hot plasma, which then begins to expand at normal, non-exponential speeds. Because the space between these bubble universes is still inflating exponentially, it grows far faster than the bubbles themselves can expand. Even though bubble universes are constantly forming, the inflating space between them stretches so rapidly that it creates vast new regions of inflating space faster than decay can destroy them. Once eternal inflation begins in a region, it creates a self-sustaining engine of creation. Floating high above that cosmic ocean, you would see a sea of inflating space, dotted here and there with isolated pockets of light. Each one a distinct universe growing within its own local sky. Our entire observable universe. Everything we can detect with our most advanced telescopes across 93 billion light-years of space would be merely one single bubble within this infinite ocean. To an observer standing inside our bubble, looking out at the sky, the universe appears uniform, complete, and endless. The Big Bang of our local history was simply the moment when inflation decay came to a stop in our specific patch of space, filling our sky with warmth and particles. Outside our bubble, across distances so vast that light can never bridge the gap, other bubble universes continue to form. An endless archipelago of light islands of matter and stars separated by vast expanding channels of dark space that light itself can never cross. Some of these pocket universes might share our familiar physical laws. Others, born from different decay states of the inflation field, might possess subtly different properties, varying strengths of gravity, different masses for subatomic particles, or different dimensions of space. The concept of eternal inflation bridges the gap between cosmology and fundamental particle theory. But it presents a deep challenge to how we test scientific ideas. Because the space between bubble universes expands faster than light, we cannot travel or send signals to another pocket universe. We are bound within our own bubble horizon. The existence of other universes cannot be verified by taking a direct photograph or sending a probe across the boundary. Yet, scientists search for indirect signatures. If two bubble universes formed close together in the early stages of eternal inflation, their expanding horizons might have touched briefly before inflation pushed them apart. Such a collision would leave a subtle, circular distortion imprinted on the cosmic microwave background radiation in our sky, a physical bruise left by another universe touching our own. Whether these cosmic bruises exist remains a subject of careful observational research. As we ponder this endless ocean of expanding potential, our view of reality expands from a single island to a vast cosmic archipelago. The universe we inhabit becomes part of a far grander construct, a multiverse, the cosmic archipelago. Imagine standing on a high mountain ridge at midnight, looking out across a landscape of rolling valleys. In the valley directly below you, a warm village glows with golden lights. Beyond the next ridge, another valley lies completely dark. Further still, a third valley is veiled in thick white mist. Each valley forms its own distinct microclimate. One is cold and windy, another is still and warm. Yet all of them exist within the same mountain range, carved from the same stone under the same sky. For generations, physics assumed that our universe had no neighboring valleys. We believed that the constants of nature, the strength of gravity, the mass of an electron, the speed of light, were unique, rigid, and inevitable. We hoped that a single master equation would one day prove that the universe had to be structured exactly as we observe it. Theoretical physics, particularly string theory, has led us toward a very different realization. Rather than a single fixed set of laws, the mathematics reveals an immense terrain of physical possibilities known as the string theory landscape. In string theory, the fundamental building blocks of nature are not point-like particles, but microscopic strings of vibrating energy. For these equations to work, strings must vibrate across extra-spatial dimensions. 6 or 7 dimensions curled up into geometric shapes far too small for our instruments to detect. The specific geometry of those curled-up dimensions dictates the physical laws of the surrounding space. One shape produces strong nuclear forces, another shape weakens gravity to a faint trickle. When physicists calculated the total number of possible ways these extra dimensions could be folded, they arrived at a number beyond human intuition, roughly 10 to the power of 500 distinct geometric configurations. Each configuration represents a different valley in the physical landscape, a distinct set of laws waiting to be realized in space. A mountain valley resting in silence. In one valley, gravity pulls so fiercely that stars burn out in 1,000,000 years. In another, particles never bind together, and matter drifts in cold, endless clouds. When the string landscape is combined with eternal inflation, the result is a multiverse of incredible variety. As eternal inflation stretches space across eons, different regions decay into different valleys of the landscape. One bubble universe forms with extra dimensions folded in one shape, while a neighboring bubble forms with a completely different geometry. The multiverse becomes a physical reality, where every mathematically allowed set of physical laws finds a home in a real pocket universe. In the vast majority of these pocket universes, the conditions are hostile to structure. If gravity were slightly stronger, space would collapse into black holes long before gas could condense into suns. If the electromagnetic force were slightly different, chemical bonds would fail, and atoms could never form molecules. This brings us to a quiet realization known as the anthropic principle. We find ourselves in a universe with laws exquisitely tailored for complexity, chemistry, and life. Not necessarily because our cosmos was custom designed, but because we could only emerge in a valley where the climate allowed observers to exist. Walking through a forest of millions of trees, you do not marvel that you are standing under one that provides shade. You sit beneath it because that is where shelter is found. The multiverse hypothesis remains one of the most fiercely debated ideas in modern science. Critics argue that if neighboring pocket universes lie beyond our cosmic horizon, forever unreachable by light or signals, the theory loses its scientific testability. If a concept cannot be falsified by experiment, does it remain science, or does it cross into philosophy? Defenders maintain that the multiverse is not an arbitrary hypothesis invented to explain away fine-tuning. It is a direct mathematical prediction emerging from inflationary cosmology and string theory frameworks built to explain the physics inside our own sky. Whether our universe is a solitary sanctuary or one island in an infinite archipelago, the perspective it offers is humbling. The starlight reaching your eyes tonight is a local phenomenon, a journey measured across light years within our specific valley of space. The rules that govern the fusion inside those stars, the chemistry of our oceans, and the rhythm of our breath are the steady, beautiful laws of our particular bubble. The sky remains open, silent, and deep. The stars shine peacefully across the dark, drifting along the calm curvature of space, carrying their ancient light into the quiet future. Light without scale. Imagine holding a simple photograph in your hand. Look closely at the image, a calm, dark horizon under a canopy of stars. Now imagine shrinking that photograph down until it fits on the head of a pin. Then imagine enlarging it until it spans the width of an ocean. If the photograph contains a scale bar, a ruler telling you that 1 centimeter equals 100 kilometers, your mind can immediately calculate its size. But if you remove the ruler, remove the trees, the buildings, and every familiar landmark, size becomes a relative illusion. Without a reference point, a microscopic dot and a vast expanse become geometrically indistinguishable. In theoretical physics, this fluid relationship between scale and geometry forms the foundation of one of the most audacious cosmological models ever proposed, conformal cyclic cosmology. Conceived by Nobel laureate Sir Roger Penrose, this theory asks us to look past our traditional assumptions about beginnings and endings, inviting us to examine what happens to space when physical clocks and rulers cease to exist. To understand Penrose's vision, we must travel far into the future of our universe, trillions upon trillions of years from now. Long after the last stars have burned through their nuclear fuel, the night sky will grow cold and dark. Galaxies will disperse into the expanding void. Black holes, which once anchored the centers of star clusters, will slowly decay through Hawking radiation, evaporating over eons until they too vanish into faint flashes of light. Picture that far future cosmos, an immense quiet continuum populated only by photons and massless particles, drifting through a cold, boundless expanse. Here, nature presents us with a profound physical paradox involving the nature of light. Particles with mass, like electrons and protons, possess rest mass. They experience the passage of time. They move slower than the speed of light, carrying an internal clock that marks the ticking of eons. They give the universe a sense of scale, defining what is large and what is small. Light, however, is made of photons. Photons have zero rest mass. Because photons possess no rest mass, they do not experience the passage of time or distance in the way massive matter does. For a photon, emission and absorption occur without temporal separation. In a cosmos populated entirely by massless particles, there are no physical clocks left to measure time, and no physical rods left to measure distance. When a universe loses all particles with rest mass, it loses its sense of physical scale. Mathematically, when scale dissolves, an infinitely stretched, cold, and vast universe becomes geometrically equivalent to an unimaginably tiny, dense, and hot state. The boundary between infinite expansion and a subatomic origin vanishes. Penrose demonstrated that through a mathematical transformation known as conformal geometry, the far future end of one universe, which he calls an eon, can be smoothly mapped onto the Big Bang of the next. In conformal cyclic cosmology, the Big Bang was not a moment of creation out of nothingness, nor was it a physical bounce caused by spatial compression. It was a geometric transition, a seamless rescaling of reality as time and distance lost their meaning. What makes Penrose's model remarkable is that it does not remain purely theoretical. It offers a specific, testable prediction in our sky. During the final stages of a previous eon, supermassive black holes would occasionally collide, releasing immense bursts of gravitational radiation. As those gravitational waves traversed the fading universe, they would leave subtle, concentric ripples imprinted on the massless light of that ancient sky. When that eon transitioned into our own, those geometric ripples would be carried across the boundary, leaving faint, circular temperature variations embedded in our cosmic microwave background. Penrose and his colleagues claim to have detected these subtle concentric rings in space telescope data, calling them Hawking points. Imagine standing under a midnight sky, looking at invisible ancient circles woven into the background, radiation faint footprints left by giant black holes that merged in an eon before our own. Mainstream astrophysics remains cautious regarding Penrose's claims. Many cosmologists argue that the statistical patterns identified as Hawking points can be explained by standard inflationary physics or random noise in the observational data. The debate continues as new, higher-resolution sky maps are analyzed. Whether Penrose's model is ultimately verified or disproved, it forces us to confront the deep flexibility of physical geometry. It suggests that what we perceive as absolute boundaries, the beginning of time, the end of space, may simply be perspectives shaped by our reliance on physical clocks and rulers. The sky above us remains motionless and deep. The ancient light of distant suns continues its journey across the dark, marking our place within a continuum whose ultimate boundaries we are only beginning to comprehend. The invisible threads. Imagine sitting beside an ancient stone bridge spanning a wide, slow-moving river at dusk. Watch the water flow beneath the arches. You cannot see the deep wooden pilings driven into the riverbed below the surface. They are submerged in dark mud, hidden from view. Yet, as you watch the heavy stone arches hold their ground against the pulling current, you know those pilings are there. Without their hidden strength, the stone would crumble, and the bridge would wash away into the river. For nearly a century, astronomers studying the cosmos have encountered a similar, unsettling truth. The universe we see is held together by something we cannot detect. When we point our telescopes toward distant spiral galaxies, we see magnificent wheels of billions of stars, swirling in delicate cosmic dances across light years. By measuring the light emitted by these stars, we can calculate the total mass of visible matter within a galaxy: the gas, dust, and glowing suns. According to the laws of gravity established by Isaac Newton and Albert Einstein, the orbital speed of a galaxy's outer stars depends directly on the amount of mass enclosed within its structure. Stars near the center, where mass is concentrated, should orbit quickly, while stars at the outer edges should orbit much more slowly. In the 1970s, astronomer Vera Rubin conducted precise measurements of galactic rotation speeds. What she discovered shattered conventional astrophysics. Outer stars were not slowing down. They were moving around galactic centers at the exact same high speeds as inner stars, moving so fast that the gravitational pull of all visible matter combined was far too weak to hold them in orbit. By all known laws of motion, these galaxies should have flown apart, scattering their stars into the deep void billions of years ago. Yet they remained intact, turning smoothly across the dark, an unseen hand holding the spinning wheel together. A massive, silent halo of hidden material wrapping around every galaxy, binding its stars to a shared center. To explain this cosmic anomaly, physics was forced to accept a startling reality: visible matter. Everything that forms stars, planets, oceans, and living beings makes up less than 15% of all matter in the cosmos. The remaining 85% consists of an unknown, non-luminous substance known as dark matter. Dark matter does not emit, absorb, or reflect light. It does not interact with electromagnetic radiation in any way. It passes through ordinary matter, like phantom dust, completely invisible to our most sensitive light detectors and radio dishes. We know it exists solely through its gravitational footprint. It bends the paths of light passing near it, shapes the rotation of galaxies, and draws ordinary gas together into the giant cosmic web we observe today. Consider the role dark matter played in the early history of space. In the eons following the Big Bang, ordinary matter was hot, energetic, and tightly coupled to radiation. As space expanded, this radiant pressure prevented ordinary gas from collapsing into dense structures. Dark matter, unbothered by radiation, began to clump together under its own gravity much earlier. It formed a vast subterranean scaffolding, an invisible network of long filaments and dense nodes stretching across the expanding void. Picture a dark, weightless web stretching through space, its invisible threads pulling primordial gas into its deepest channels, seeding the universe with the very first stars. Without this invisible dark matter scaffolding, ordinary gas would have dispersed too thinly across space. Galaxies would never have formed, stars would never have ignited, planets would never have coalesced in the dark. Every glowing star cluster we photograph today is an island of light resting inside a massive, submerged iceberg of dark matter. Yet, despite decades of research using deep underground detectors and particle accelerators, the true physical identity of dark matter remains one of the greatest mysteries in modern science. Physicists hypothesize that dark matter is composed of as yet undiscovered subatomic particles, such as weakly interacting massive particles or axions born in the extreme energies of the early cosmos. These particles would interact only through gravity and the weak nuclear force, floating through space like a silent, ghostly ocean. Underground detectors, built deep within subterranean salt mines and shielded by kilometers of solid rock, sit waiting in silence for a single dark matter particle to collide with a crystal lattice. Above, space telescopes map the gravitational distortions left by this hidden mass across billions of light-years. A quiet vigil held beneath the Earth. Instruments waiting in subterranean stillness to catch the softest touch of a ghost particle that shaped the night sky. As we map the large-scale structure of the cosmos, dark matter reminds us of the profound limits of human perception. Our eyes evolved to see light, Yet light is merely a rare, luminous decoration on a universe built primarily from hidden architecture. The night sky remains undisturbed, holding its ancient secrets. Distant galaxies turn silently across the velvet dark, guided by unseen forces, carrying their light forward through an invisible fabric whose deeper nature we are still striving to understand: the phantom force. Imagine sitting in a small rowing boat in the middle of a calm, motionless lake. You pull the oars back, glide forward a few meters, and then resting your arms, you watch the water gradually slow your momentum. Naturally, you expect the boat to come to a peaceful standstill. Now imagine that instead of slowing down, your boat begins to glide faster. Without any wind, without any current, and without any effort from your oars, the boat accelerates across the water, moving faster with every passing second, drawn outward by an unseen, silent force. For decades, cosmologists assumed the expansion of the universe would behave like that coasting boat. The Big Bang had provided the initial outward push. Gravity, the universal attractive force exerted by every star, planet, and cloud of dark matter, acted like the friction of the water, quietly pulling space inward, slowing the cosmic expansion over billions of years. In the late 1990s, two independent teams of astronomers set out to measure how much gravity was slowing down the cosmos. They used distant exploding stars, known as Type Ia supernovae, as cosmic light meters. Because these stellar explosions shine with a known, uniform brightness, measuring their light reveals both their distance and how fast space has expanded since the explosion occurred. What the astronomers discovered shocked the scientific world. Distant supernovae were fainter than expected. They were much farther away than gravity should have allowed. Space was not slowing its expansion. Roughly 5 billion years ago, the cosmic expansion shifted gears. The universe began expanding faster and faster, accelerating outward into the dark. A subtle, repulsive pressure woven into the very vacuum of space. An invisible force overpowering the gravity of billions of galaxies, pushing the horizon farther away with every passing heartbeat. To account for this unexpected acceleration, physics introduced the concept of dark energy. Unlike dark matter, which pulls material together through gravity, dark energy acts as a repulsive force, pushing space apart. And while dark matter clumps around galaxies, dark energy is smooth, uniform, and pervasive, filling every cubic meter of empty space equally. Today, precise measurements from space telescopes reveal a humbling census of reality. Ordinary matter. Everything that forms rocks, light, and living tissue makes up roughly 5% of the universe. Dark matter accounts for 27%. The remaining 68% consists of dark energy. Nearly 7/10 of everything that exists is a smooth, mysterious pressure embedded within the vacuum itself. Albert Einstein had actually predicted a similar phenomenon decades earlier. In his equations of general relativity, he included a mathematical factor called the cosmological constant, an inherent energy density belonging to empty space itself. In quantum field theory, empty space is never truly void. It hums with virtual particles continuously appearing and disappearing. This zero-point energy creates an intrinsic pressure that pushes outward on the fabric of space-time. As the universe expands and grows larger, the density of matter drops because the same number of atoms are spread across a bigger volume. But dark energy does not dilute, because it is a property of space itself. As more space is created, more dark energy emerges to fill it, maintaining a constant outward pressure. A quiet ocean whose waters never shallow, where expanding space continually creates its own depth, driving its shores endlessly farther apart. The ultimate destiny of our cosmos depends entirely on the nature of this phantom force. If dark energy remains constant, the universe will continue to accelerate forever. Billions of years from now, distant galaxies will be pushed beyond our horizon, traveling away faster than light can cross the intervening distance. The night sky will slowly drain of extragalactic light. Neighboring galaxies will merge into a single, isolated island of aging stars, surrounded by a vast, empty dark. Yet, dark energy remains an unsolved puzzle. We do not know if its density is truly fixed or if it will evolve over eons. And while this silent pressure pushes galaxies apart across light years, gravity retains its total dominion in localized pockets of space, compressing matter so intensely that space breaks down completely inside the geometry of black holes. The geometry of black holes. Imagine walking across a wide, frozen lake on a winter night. The ice beneath your feet is smooth and solid. As you take each step, you can look ahead and choose to walk in any direction, north, south, east, or west. Time carries you forward into the evening, but your path through space remains entirely under your control. Now suppose that as you walk toward the center of the lake, the ice begins to slope gently downward, curving toward a deep, unseen hollow. As you step closer to the center, the slope grows steeper. Soon, the curvature becomes so extreme that every direction you look forward, backward, left, or right leads downward into the central hollow. To step in any direction is to step toward the bottom. Space itself has been bent so severely that all paths converge on a single point. In general relativity, this extreme curvature is not an imaginary exercise. It is the physical reality of a black hole. When a massive star exhausts its nuclear fuel, it can no longer support its own weight against gravity. In its final moments, the star collapses inward. If the remaining core is sufficiently massive, no known force in nature can halt the collapse. Matter is squeezed into a region smaller than its own gravitational radius. Space curves inward around the collapsing core until a boundary forms, a spherical horizon known as the event horizon. The event horizon is not a solid surface made of stone or ice. It is a mathematical edge in space-time, a point of no return, a threshold in the dark where the escape velocity equals the speed of light, a boundary beyond which no signal, no particle, and no beam of light can ever return to the outside world. Outside the event horizon, space curves gracefully. If you were to hover in a vessel near a black hole, you would see the light from distant background stars bent and distorted around its silhouette, forming brilliant rings of distorted starlight known as Einstein rings. Because gravity warps time, clocks closer to the black hole tick significantly slower than clocks farther away. If an observer were to drop a glowing beacon toward the event horizon, someone watching from a safe distance would see the beacon's descent slow down as it approached the edge. The light from the beacon would stretch into longer, redder wavelengths, fading into a dim glow, appearing to freeze forever at the horizon. For the beacon itself, however, time passes normally. It crosses the event horizon without stopping, entering a region where the geometry of space-time undergoes a radical inversion. Inside the event horizon, space and time swap their physical roles. In ordinary space, you are free to move forward or backward in spatial directions, but you are forced to move forward in time toward tomorrow. Inside a black hole, the radial direction toward the central singularity becomes time-like. Moving toward the center is no longer a choice of direction. It becomes as inevitable as moving into the future. Every path, every beam of light, every subatomic particle inside the event horizon points inexorably toward the central singularity, a point where classical general relativity predicts infinite density and infinite spatial curvature, a place where space ends and classical equations fall silent. a microscopic boundary holding secrets that challenge our understanding of reality. For decades, black holes were viewed as ultimate cosmic vaults, destinations where information entered and was erased forever from the universe. Yet, when quantum mechanics is applied to the quiet geometry of the event horizon, these dark vaults reveal a subtle, unexpected activity, one that sparks a deep paradox about the preservation of information itself, the information paradox. Suppose you write a detailed letter on a piece of paper, a record of your thoughts, memories, and observations. You place the letter inside a fireplace and set it alight. As the paper burns, it turns to grey ash, while smoke and heat rise into the air. To your eyes, the information written on the page has been destroyed. Yet, according to the fundamental laws of quantum physics, that information is not lost. In principle, if you could collect every grain of ash, every particle of smoke, and every photon of heat released by the fire, you could use the laws of physics to reconstruct the original text. Quantum mechanics mandates that information can be scrambled, but it can never be truly erased from the cosmos. This principle is known as quantum unitarity, the law that the quantum state of a closed system at any moment determines its past and its future. In the mid-1970s, theoretical physicist Stephen Hawking discovered a conflict between this quantum law and the geometry of black holes, sparking a debate that would reshape modern physics. Hawking studied how quantum fields behave near the quiet boundary of an event horizon. As we explored in earlier chapters, empty space is filled with quantum fluctuations, virtual particle pairs that constantly pop into existence, interact, and annihilate each other back into the vacuum. Hawking calculated what happens when a virtual particle pair forms right on the edge of an event horizon. One particle falls across the boundary into the black hole, while its partner escapes into outer space, carrying away a tiny fraction of the black hole's energy. To an observer far away, this escaping particle appears as thermal radiation, a faint glow now known as Hawking radiation. Because the escaping particle carries away energy, the black hole slowly loses mass. Over unimaginably long timelines, a black hole will gradually shrink, emitting radiation until it completely evaporates into space. Here lies the profound paradox. Hawking's original calculations showed that this escaping radiation was purely thermal, completely random, featureless heat, carrying no memory or record of the matter that originally fell into the black hole. If a black hole forms from a complex star, absorbs planets, computers, and books, and then evaporates entirely into featureless thermal radiation, all the information contained within those objects would be permanently erased from reality. This creates a clash between two pillars of modern science. General relativity dictates that nothing can escape from inside an event horizon, implying that information swallowed by a black hole is trapped forever. Quantum mechanics dictates that information can never be destroyed. Both theories cannot be correct in their standard forms. A fundamental conflict at the frontier of knowledge. A paradox forcing physics to rethink the nature of space, entropy, and reality. For decades, theoretical physicists struggled to resolve this black hole information paradox. In recent years, breakthroughs in quantum gravity and string theory have offered a startling solution known as the holographic principle. This principle suggests that when an object falls into a black hole, the information it carries does not sink into a central point. Instead, it becomes encoded on the two-dimensional surface of the event horizon, like a complex hologram. As the black hole slowly evaporates, subtle quantum entanglements between the horizon and the outgoing Hawking radiation allow that encoded information to leak back out into space, scrambled but intact. If the holographic principle holds true, it implies something profound about our broader universe. Three-dimensional space, as we experience it, may be a projection. an illusion generated by quantum information encoded on a distant two-dimensional boundary, a cosmic hologram, where the geometry of space emerges from the quiet weaving of subatomic information. The study of black holes has transformed these dark cosmic vaults from dead ends into fundamental laboratories for theoretical physics. By pushing our laws to their absolute limits, they guide us toward the ultimate goal of modern science, a unified theory of quantum gravity. The night sky remains undisturbed and deep. Far out in the dark, black holes turn quietly, holding their event horizons against the void, guarding secrets that bridge the world of the atom with the architecture of the cosmos. And as we seek to bridge these two worlds, we face the ultimate quest in modern physics: the search for a single, elegant framework capable of unifying gravity and quantum mechanics into a theory of everything. The unification quest. Imagine standing inside a magnificent cathedral built over centuries. Look up at the vaulted ceiling. You see massive stone arches curving gracefully through the air, anchored by solid granite columns. The architecture feels permanent, structured, and predictable, designed around clear geometric symmetry and balance. Now, step closer to one of those stone pillars. Imagine pulling out a powerful microscope and zooming in past the surface of the granite, past the crystal grains, past the molecules, down to the subatomic particles forming the stone. Here, the orderly cathedral vanishes completely. In its place is a chaotic, shimmering world where particles pop into existence and disappear, where energy fluctuates unpredictably, and where certainty gives way to probability. For more than a century, modern physics has operated with two completely different rulebooks to describe these two realms. To describe the grand cathedral of the large-scale universe, galaxies, stars, planets, and the curvature of space, we use Albert Einstein's general relativity. It is a smooth, deterministic theory where space-time bends predictably under the weight of mass. To describe the subatomic chaos within the stone atoms, electrons, and fundamental forces, we use quantum mechanics. It is a probabilistic granular theory where particles do not occupy fixed positions until observed, and where empty space churns with quantum noise. Individually, both theories are astonishingly successful. General relativity accurately predicts the orbits of planets, the bending of starlight, and the expansion of the cosmos. Quantum mechanics powers our modern electronics, lasers, and nuclear physics. Yet, when we attempt to combine these two theories into a single mathematical framework, the equations clash violently, yielding nonsensical answers like infinite probabilities and meaningless infinities. Nature, however, operates as a single, coherent reality. The cosmos does not switch rulebooks when an atom joins a star. The single, quiet tapestry woven from an underlying thread, a hidden framework waiting to be discovered, where the geometry of space and the dance of the atom speak the same physical language. This search for a single, overarching framework is known as the quest for quantum gravity, often called the theory of everything. The core reason these two theories clash lies in how they view the stage of reality. In quantum mechanics, space and time are treated as a fixed, passive backdrop, a stage upon which subatomic particles perform their dance. In general relativity, space and time are not a static stage. Space-time is an active participant that curves, stretches, and dynamically responds to matter. When you try to apply quantum principles to space-time itself, the smooth fabric of Einstein's universe begins to boil at extreme microscopic scales, forming a violent, chaotic state known as quantum foam. Physicists have developed several creative mathematical avenues to resolve this conflict. The most prominent candidate is string theory. As we explored when examining the cosmic landscape, string theory proposes that fundamental particles are not zero-dimensional point dots, but microscopic vibrating filaments of energy. Just as different vibrations of a violin string produce different musical notes, different vibrational modes of a fundamental string manifest as different particles. An electron, a photon, or a graviton. The hypothetical quantum particle of gravity. By replacing point particles with extended strings, string theory smooths out the violent mathematical infinities that occur when gravity is quantized, uniting all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces, into a single musical framework. Another major approach, loop quantum gravity, takes a different path. Rather than trying to explain all forces and particles, it focuses strictly on quantizing space itself, weaving geometry from discrete, microscopic loops without assuming a fixed background stage. More recent frontiers explore concepts like quantum entanglement and spacetime emergence. The radical idea that space itself is not fundamental, but an emergent property born from quantum information network interactions, much like temperature emerges from the collective motion of unseen atoms. Imagine space as a tapestry woven from strands of pure quantum information, where distance, gravity, and geometry are merely the macro patterns formed by microscopic entanglements. Despite decades of brilliant mathematical progress, the quest for quantum gravity faces a humbling hurdle: scale. The quantum structure of space is thought to manifest at the Planck scale, a domain trillions of times smaller than a single proton, operating at energies far beyond the capabilities of any particle accelerator human technology could ever build. Because we cannot build a collider large enough to probe the Planck scale directly, physicists look to the natural laboratories of the cosmos. We look to the extreme environments where quantum mechanics and immense gravity were forced to interact in reality, the ultimate centers of black holes, and the very first fraction of a second during the origin of space. If subtle quantum gravity effects occurred during the primordial dawn, they may have left delicate, microscopic signatures imprinted on the cosmic background radiation or in the patterns of primordial gravitational waves traversing space. Researchers continue to analyze sky data, searching for those faint, ancient footprints. A quiet telescope listening to the deep night, waiting for a whisper from the first moment of time to reveal the hidden code of geometry. As theoretical physics continues to build these mathematical bridges, we are reminded that our search for unification is an ongoing journey. We are attempting to read a book whose first pages were written in a language we are still learning to translate. Yet every equation written, every satellite launched, and every theoretical model explored brings us one step closer to understanding the underlying coherence of reality. And as we stand at this frontier of knowledge, looking out across the vast, expanding architecture of space, we naturally return to the question that started our journey: confronting the final limits of what human minds can truly know about the cosmos, the unanswered sky. Imagine returning once more to that quiet edge of the vast, motionless body of water where our journey began. The night is still. The air remains cool and fresh. The soft, rhythmic sound of water meeting the shore continues its slow, unhurried cadence, untroubled by the passage of hours. Up above, the canopy of the night sky stretches out in absolute silence, filled with its distant silver points of light. We have traveled far across the landscape of modern cosmology. We have explored the expansion of space, the south pole of time, the quantum engine of inflation, and the ancient echo of the first light. We have journeyed through cyclic universes, quantum bounces, eternal oceans, string landscapes, and the dark forces shaping the void. Yet, as we sit under this open sky, a quiet realization settles into the mind. After all our equations, after all our observations, the cosmos remains vast, deep, and beautifully incomplete. There are questions that modern physics still cannot answer. We do not know why the universe exists instead of nothingness. We do not know what triggered the initial quantum state, why the laws of physics take the precise forms they do, or whether our observable sky is a solitary sanctuary or an ephemeral bubble in an infinite multiverse. We do not know the ultimate identity of dark matter, the true destiny of dark energy, or how the subjective light of human consciousness arises from the physical atoms forged inside ancient suns. A vast, open book resting under the night, where every page we turn reveals 10 new pages waiting to be read in the quiet dark. It is easy to view these unanswered questions as limitations of science, but in truth, they are the very heart of the scientific spirit. Science is not a rigid monument of static facts. It is a living, evolving dialogue between human curiosity and the natural world. It is a willingness to stand at the edge of the unknown and say, without fear or discomfort, we do not yet know. Throughout history, every major leap in our understanding, from discovering that the Earth orbits the Sun to learning that space is expanding, began at a point where traditional answers proved insufficient. Uncertainty is not a wall that blocks our path. It is the open door that invites us to keep looking, to keep building instruments, and to keep asking quiet questions under the stars. Consider the remarkable journey that brought us to this moment. We're small, fragile beings, living on a tiny, rocky world, drifting around an ordinary star in the suburb of a spiral galaxy. Our bodies are composed of stardust, carbon, iron, oxygen, and nitrogen forged in the nuclear furnaces of ancient suns that died billions of years ago. Through us, the cosmos has developed a way to think, to measure, and to wonder. When we look up into the night sky, it is the universe looking back at itself, pondering its own origins, decoding its own geometry, and reflecting on its own deep time. Stardust waking up to look at the stars, a brief conscious spark holding a mirror to the infinite expanse that birthed it. As you rest in the quiet stillness of the night, consider how comforting this cosmic perspective truly is. The problems of our daily lives, while real and meaningful to us, exist within a brief, fleeting moment on a tiny world. Beyond our immediate horizons lies an expanse that has been unfolding for nearly 14 billion years. A reality structured by physical laws of deep elegance, carrying secrets far larger than our immediate worries. The universe is not a closed, finished story whose final line has been written. It is an active, living mystery, vast, peaceful, and open to the future. There is no need to rush toward every answer tonight. The cosmos has taken billions of eons to reach this moment, and it will continue its calm expansion for eons to come. The night air remains motionless and still. The faint murmur of the water continues its steady rhythm along the shore. Up above, distant stars shine with quiet permanence, casting their ancient light across light years, traveling through the calm, stretching expanse of space. The sky remains open, dark, and peaceful. Sleep well under the quiet expanse of an unanswered cosmos.